This is a lecture for Chapter 5. It's called Extending Regression. Really what it's about is just understanding how categorical predictors fit in to a regression model. What's awesome about it is that they can be integrated with very little change in how it works. Basically, the regression is doing the exact same thing it did before. We're just going to change the words that we use to interpret it. So when we do categorical predictors, there's other names for it. There's ANCOVA when you have covariates included, a t-test when you just have a single two-level predictor, ANOVA if you have two or more levels. All of these are just regression, just with specific names tied to them. So when it comes to the actual interpretation when you're using a categorical predictor, the line still goes through the conditional mean just like before, but now the conditional mean is at a very discrete point. Instead of having points between 0 and 1, now we just have points at 0 and points at 1. And at 0, these individuals are male, and at 1, these individuals are female. So this line is still going through the mean. So this is the mean for males right here, and this is the mean for females. This 0-1 thing that we're doing is called dummy coding. I'm not sure why they picked that name, but it's called dummy coding. You essentially pick a reference group, which is the 0 group. In this case, it's male. And then you're essentially seeing how non-reference groups, like female here, differ from that group. And in this case, the slope that we have here, it's the same as what we have always done. For a 1 unit change in sex, there's whatever the slope is, change in y, in the outcome. But it sounds weird to say that when it's a discrete variable. What's a 1 unit change in male mean? So it's weird to say it that way. And so what we say instead is we actually interpret it as this is the difference from females to males. So it's still doing the same thing. That's what I'm trying to stress here, is that it's doing the exact same thing we did before, but this time we're going to interpret it differently. We're going to talk about differences between the groups. So consider this example. When we dummy code, there's always a reference group. So you either pick it yourself or you let R do it. R is going to pick whatever one is 0 or whatever one is lower alphabetically if it's not a factor. In the output below, we coded it in such a way that males were the reference group and we're comparing females to that group. The estimates of the dummy variable are the mean differences from that group. So down here, it says sex female. So female is the group that we're comparing to the reference group. The reference group will not be on here. So one thing to consider, why do we need a reference group? Well, when you have discrete variables, you have to have something to compare to. When you have a continuous variable, you can just say for a 1 unit increase and it can be from anywhere. But when it's discrete like this, you need a starting point. And it can be any of the groups that you pick, but it needs to be 1. So in this case, sex female, they are 0.137 units lower on the outcome than males. So that's how we'd interpret this number right here. It turns out that's not significant, so we would say there's no significant difference between males and females and whatever our outcome is. But on average, in our sample, females were just slightly lower on whatever this is. You can look at this from a predicted value standpoint. So same model, we're just plugging in these values into the equation. So we have 0.0069, so I just put 0.007 minus, because this is negative 1.38 times sex. And so you might ask, how do you times it by sex? It's male and female. Well, the model doesn't see it as male and female. It just sees it as zeros and ones. When the person is male, which is dummy coded as 0, we get this equation where this is times by 0 because 0 is for male. So the predicted value for males is 0.007 on this scale, whatever it is. With that in mind, can you think of what we would do to calculate it for females? If you thought, let's plug in the 1 because that's what the females were coded as, you're exactly right. So now we have the same equation, but we're plugging in 1 here. And so this is the predicted value for females. So in other words, other ways we can say this, males and females means differ by the estimate of negative 0.138, or the predicted value of males and females differ by the estimate of negative 0.138, or females on average are 0.138 units of y lower than males. Of course, in this example, it wasn't significant, but just trying to get in your heads what these differences mean, what those estimates mean. So a quick note about dummy coding. So if we have a variable with 2 levels, we have a single dummy coded variable. In the sex example, we have 2 levels, and all we had was 1 variable, and it was female. And so if the person was female, they got a 1. If they weren't, they got a 0. So it's just 1 variable. We would never make it 2 variables, because 1 indicator for females and another for males would mean we already have that information. So consider this. If we know if someone is female and the only other option in the data is male, what more information could we get if we had another indicator? Turns out nothing. If we know they're not female, then we know they're male in this data set. So if you actually had 2 variables, they would totally cancel each other out. They would have perfect collinearity. The information in one is perfectly contained in the other. Don't do it, don't. So when you have 2 levels, you have 1 dummy variable. So think about, what if you have 3 levels? If you have 3, you have 2 dummy variables, because 2 will give you all the information you need for the 3 groups. Because if you know they're not in one group and you know they're not in the other group, you know they're in the 3rd group. So it'll always be that way. The number of levels minus 1 is how many dummy variables you need. One thing that's nice, one note, is that R automatically creates these. So it's not something you're going to have to think about too much. You just need to be aware that's how it works. When we do multiple regression with dummy variables, you can actually have dummy variables with other dummy variables. You can have it with other continuous variables. This is one example where we have x, it's a continuous variable, and we have y, our predicted value. And we also have sex, male or female. And so we actually can see on average, as people go up on x, they go up on pred. But we also can see that it looks like there's a bit of a difference between males and females on this variable. So one way that you can think about this is when you have one dummy variable, it essentially just changes the intercept. So in this case, the line for females, its intercept when it crosses wherever 0 is, 0 is right here, it's higher than the intercept for males. So when you have a dummy variable, you can still have continuous variables having lines. It just changes where the intercept is for those groups. Another thing, do not standardize categorical predictors. So a categorical predictor is already, it has an interpretable meaning. It's a comparison between groups. When you standardize that, it totally changes that from comparing two groups to something that's much, much harder to define. Another thing to consider, have you ever tried to make a numeric variable categorical so you could use ANOVA? I did this a ton when I was learning how to do stats early on as an undergrad and early grad. I would try to fit it to the stuff that I knew. But what's interesting is that it's less powerful. It throws away information. It treats similar people as though they were different, and it increases measurement error. Those are all bad things. For example, I bring up this question, what about clinical depression and cutoff points? So in a situation where, let's say we're looking at depression, there are going to be some clinical measures where they say this is where it becomes problematic. This is a clinical issue at this point. So sometimes creating a categorical variable from a numeric can be useful. But most of the time what it ends up doing is you have a random cutoff point or arbitrary. And let's say our cutoff point on our scale was 5. So what we're saying is person with a score of 4.5 and a person of 5.5 is very different, while someone with 5.5 and 10 is the same, and someone with 0 and 4.5 are the same. When we chop up a numeric variable, we're arbitrarily saying some people are more alike than others. When it makes sense, you want to use a numeric variable as numeric, not as categorical. Another thing, regression to the mean. So the name of regression actually comes from this. It's the idea that extreme values in one variable are often associated with values closer to the mean in the other variable. So for example, let's go back. So this line right here, this would be the expected line if there was no such thing as regression to the mean. Because this super extreme point on father's height should also be just as extreme for son's height. But it turns out the true best fitting line is this one, and it accounts for regression to the mean. What this means is someone that has a really short father, their son, on average, the average down here is right here, not as short. Same thing happens on the extremes of the father's height when you're really tall. So tall fathers don't necessarily have as extremely tall sons. On average, it's actually a little lower. And the case could also be made the other direction. So extreme cases for the son's height is going to be associated with less extreme cases with the father's height. This is a phenomenon that we see in just about every part of life in the natural world. And it feels weird sometimes, but it's just the case. Regression to the mean happens when you have a really extreme point on one variable. It's associated with a less extreme or closer to the mean point on another. So why even talk about regression to the mean? I mean, it's cool, right? But it actually has some implications for what we do. So for one thing, if you're looking at difference scores, so your outcome is, let's say, the difference between pre-test and post-test scores. This actually helps us know that we need to control for the initial score as a covariate, even if it is part of our measure of our outcome. It's weird, but it's what you need to do. So if you look at pre to post change, you need to control for pre-test scores in your model. What's cool though is regression, when used right, naturally accounts for regression to the mean. It's designed for it. You also get to interpret results where extreme values are associated with more average scores with caution, which means we don't need to look for a causal mechanism that's driving this. You'll see this, there's a curse called the curse of Sports Illustrated. Essentially, when a player gets on the cover of Sports Illustrated, they tend to do worse after that. And people are like, well, it's a pressure, it just builds up. But what it turns out is that to get on Sports Illustrated, they're usually performing at an even crazier rate, doing even better for themselves than normal. And so just by chance, they're more likely to do worse at some point. And it's often after they get all this attention. And so it's not even, it doesn't even have anything to do with the pressure. Even though we want to assign causal meaning to it, we shouldn't. Also, an aside, looking at a different score with the first score, like the pretest score as a covariate, or using the second as dependent and first as a covariate are actually identical, and you'll get the same results. So a different score, or just looking at a post-test controlling for pretest, it'll give you the same results, which is kind of cool. All right, so far we've really focused on variables that just have two levels, so it's easy to compare. There's one p-value that says whether there's a difference between the groups. But sometimes we're bringing in several levels, and we're going to talk about this a lot more. But a multidimensional set is where you are bringing in more than one variable, and you're looking at, together, these variables, do they predict the outcome? So we actually can make inference regarding a set of variables like SES variables. So we could include mother's education, we could include father's income or mother's income, we could include region of birth, things like that, all in the model. But the issue with a lot of those is they have high collinearity, and so they're going to mess with each other's single p-value. But we actually can test if together they predict the outcome. We're actually going to do that by comparing R-squared values. So R-squared when the set is in there, so the set of SES variables. We minus the R-squared of the model when you don't have that set in there. And then you're times them by a few other parameters from the model itself. And this actually gives you an F statistic. So just like ANOVA, and then you get a p-value from that. So we actually can test if multiple things explain the outcome. So what does this have to do with categorical variables? Well, sometimes we're going to want to know, does the degree that someone has earned, does that influence their income? So we may not want to compare each degree with each other or even to the reference group, but we just want to compare, does it explain income? And this is how we would do that. We're going to come back to this when we talk about multi-categorical variables. This allows us to test the relationship between a set of collinear variables and the outcome. It also allows us to test many variables with similar interpretations simultaneously without having to do them individually. So we don't have to look at each individual one, we can look at them as a group. Again, that also works for categorical variables. A few final thoughts. Here's a list of things that are kind of on the docket, things that we're going to talk about that impact our results of a model. We're going to talk about under control and over control, what singularity means, nonlinearity, interactions, or moderation is another term used for it. We're going to talk about heteroscedasticity, non-normality of errors, outliers, leverage points, influential outliers, non-interval scaling, missing data, and measurement error. We're going to hit on the majority of these as we go through the chapters. Just want to have it on your radar so that you know kind of where we're heading. So at this point, you have a lot of tools that make it possible for you to use regression. But now we're going to talk about what can go wrong and how to fix that. And a beautiful picture from Glacier National Park.